The problem is, however, that when you consider this problem in large dimensions, for example, we have seen what happens in 2 dimensions, the size of the matrices that you have to deal with and that you have to diagonalize becomes huge, becomes actually exponentially large in the dimensions, in the linear dimensions of the system. And therefore, the problem is as complicated as the problem you started with. In particular, it's pretty much useless to use transfer matrices in large dimensionalities or when the range of interactions is sufficiently large. Luckily, in that limit, there is an approximation that works very well, which is known as mean field theory. So what I would like to do now is to explain this approximation, explain why it works well in large dimensions or when the range of interactions is large, and then solve it for the easy model. All right, so let us consider an easy model defined by the following Hamiltonian. Now, and in particular, let me consider all the terms in this easy model that contain a certain spin. Let's call this spin, I don't know, sigma, right? So all the terms in this easy model that contain the spin sigma are going to be minus j over 2 sigma times the sum over neighbors, nearest neighbors of sigma, sigma I, minus b times sigma, right? So these are going to be all the terms in the Hamiltonian that contain this guy. Now, suppose now that we consider this problem in increasing dimensions. So in 1 dimension, how many nearest neighbors has a site? 2, right? In 2 dimensions, if I have a square lattice, it is 4. 1, 2, 3, and 4, right? So 4 is the number of nearest neighbors. In 3 dimensions is going to be 6. In 4 dimensions, so this is d equal 2, d equal 1, d equal 2, d equal 3 is 6. In 4 dimensions, what am I going to have? What is going to be the...
Sorry.
Yes?
I mean, what is 4 dimension exactly?
It's a, you know what is the Cartesian product of R of the real numbers 4 times? It's a vector space, right?
Sorry?
It's a 4-dimensional vector space. R4.
Oh, is it like
you know what is this?
The one you have in relativistic?
For example, yeah. So, for example, the one you have in relativistic, whatever. But in 4 dimensions. So how many, if you have a lattice, a square lattice in 4 dimensions, how many nearest neighbors you have to one site?
8?
8, yes, correct. And so on and so far, right? So you see, In 1 dimension 2, 2 dimensions 4, 6, 8. Well, it's going to be 2 by 2 by 2 by 2 d times. In a generic dimensionality d is going to be 2 by 2 by 2 d times. In other words, 2 to the power d. Now, you see that as the number of dimensions increases, the number of nearest neighbors to a site gets larger and larger. And here, what you're doing in computing this term in the Hamiltonian is sigma is summing over the magnetization of all nearest neighbors to one site. Now, you can think of, yes?
Sorry, Professor, what did you say about 2 to the power d?
Well, if you are in d dimensions, the number of nearest neighbors to one site is 2 to the power d.
I think it's not true, because in d to d, so it's not 8, but it's 6.
Sorry, can you repeat your statement?
You said that in d dimension, so we will have 2 to
the power
d.
d, yes.
But in case d equal 3, so we
Yes.
have 6, but it's not 8 at 2 to the power 3.
Ah, you're right, it's 2 times d, sorry. You're absolutely right, it's 2 times d. Sorry, I made a mistake. You see, it happens. It's 2 times d. Now it's correct, right?
Yes.
Yeah, I apologize. Sometimes even professors make mistakes, you see? Anyway, so the correct statement in any case is that the number of nearest neighbors as the dimensionality grows correspondingly, gets larger and larger. Now think about this sum sigma now. Well, this sum sigma is a sum of identically distributed variables. Each spin on a different site is essentially identically distributed from the other ones from the probabilistic point of view, simply because of translational symmetry. And therefore, what we are facing is a situation, we could think about the following. What is the probability? How is the probability of sigma, the probability distribution of sigma going to look like? Well, the probability distribution of sigma is going to look like this. Is going to have a peak around a certain average value, sigma bar, which is going to be proportional to the number of nearest neighbors that is known as coordination number, and it's a little z. So this is coordination number of the lattice. And then you are going to have the width of this distribution, sigma goes like square root is actually proportional to the square root of z of the coordination number itself, or in other words, to the number of nearest neighbors to one lattice site. Why? Because what we are essentially applying is practically the central limit theorem, right? What we are saying is that all these spins are what we have here is roughly a sum of identically distributed variables. And therefore, what we expect is that their sum is going to have a probability distribution that is strongly peaked around the average with fluctuations that scale like the square root of the number of terms in the sum, which is z in this case. Okay? So this is the logic. Let us now see where this logic takes us. Well, first of all, if we apply this logic, then it's clear that instead of this sum here, we can just substitute the average, right? And the average, sigma bar, is going to be roughly z times the expectation value of the magnetization on each lattice site. Right? So this is going to be the average of this sum, because each lattice site is going to have the same expectation value of the magnetization because of translational invariance, and therefore we are going to have this result. I guess you agree with me. Now, yes?
Yes. Actually, I have some questions like, what's the coordination number?
It's the number of nearest neighbors to one lattice site.
Oh, so Z is like 2, 4, 6, 8, and 2.
Yeah, absolutely. So in D dimensions, you have that 2 times D is equal to Z.
And why is the peak of the sigma bar is around the coordination number?
Well, so it's around the average. So it's around average sigma. But average sigma is going to be proportional to the coordination number, as you see here, right? Because average sigma, if I take an average here, what do I get? I get sum over nearest neighbors of sigma, average of sigma I. Average of sigma is always the same, so it's average of sigma times sum of nearest neighbors to sigma, which is equal to z times sigma. So you see, average of sigma is proportional to z, so that's what I meant. It's not equal to z, it's proportional to z. Clear?
Oh, so the one you wrote on the upper side should be equal, not proportional then.
Yeah, no, this is actually equal. Sorry.
Also, I have a question about the lattice stuff. So in D equals to 1, you have one-dimensional lattice, and then D equals to 2, square lattice. D equals to 3, you have cubic lattice. What happens to like the D greater than 3, like D equals to 4? What type of lattice will it be?
It's a square lattice. I don't know. I mean, you're asking me how to visualize it. I don't know how to visualize something in 4 dimensions. I don't know how to draw it.
No, actually, I'm just asking whether some people have, or I mean, of course, some people must have studied this before. But what are the terms they use for this lattice greater than 3 dimensions?
Square lattice in 4 dimensions. It's always a square lattice. I mean, a cube is a square in 3 dimensions. Or cubic lattice in 4 dimensions. Call it the way you want, but it's essentially the vector is essentially the lattice generated by the 4 orthogonal unit versors in Cartesian space using translations. So you take your 4-dimensional space, you generate a basis which is just given by the 4 unit vectors along the 4 Cartesian axis. And then you generate all other points in the lattice by just translations using these 4 vectors. And then you have a 4-dimensional cubic lattice. And you can do the same in 5 dimensions, 6 dimensions, in whatever dimensions you want, even though you're not able to draw it, because we're able to draw stuff only up to 3 dimensions. But mathematically, we can define whatever we want.
Okay, thank you.
All right. So let's move on. Now, you realize that in order for this theory to be correct, the only important thing is that the number of terms.
Sorry?
Yes?
We cannot see the screen.
You cannot see the screen? Just a second. All right. So now, in order to see, how to say, now you understand that in order to, for this theory to be correct, then the number of nearest neighbors to one site has to be large. Because when the number of nearest neighbors to one site is large, you can think of applying the central limit theorem, and then everything else will follow. You can replace the sum by z times the average, and so on and so forth. So in practice, there are 2 instances in which this happens. Either you take z to be very large, so the coordination number becomes large, which means that you consider systems in large dimensionalities. Or you take, so this is possibility number 1, or possibility number 2, you consider systems with long range interactions. Why? Because if long-range interactions are present, then each lattice point is going to interact with many others, not only the nearest neighbors, but many other lattice points, and therefore, at the end of the day, you will get mean field theory that is essentially correct. So in these 2 limits, when the range of interactions goes to infinity, or when the number of dimensions goes to infinity, mean field theory is not only an approximation, it is exact. Okay? All right, so now how to do mean field theory in practice? Well, in practice, what you do is the following. You define M as the average magnetization. And then, for each sigma I, you rewrite it in the following way as M plus sigma I minus M. So it's equal to an average value plus some fluctuations, delta Mi. Now what I'm going to do is I'll take H, which is equal to minus J over 2, sum over I, sigma J, minus B, sum over I, sigma I. And then I will substitute everywhere this expression. So in particular, we'll get that sigma I sigma j is equal to m squared plus delta mi sigma j plus delta mj sigma I plus delta mi delta mj. And now, since I'm assuming that the system is satisfying, satisfying the conditions for this approximation to be valid, and therefore fluctuations, local fluctuations with respect to the average are small, I'm going just to neglect this last term in the expansion. This is what it means in practice to do mean field theory.
So, Professor, yes? Can you repeat the last one? The last part that you speak about?
So, since I'm assuming that the system has is in the conditions in which mean field theory is a good approximation, and therefore the fluctuations with respect to the average are small, then I will keep only terms that are linear in these fluctuations, but the ones that are quadratic, I will neglect them, okay? So I will neglect this last term that is quadratic in the fluctuations, okay?
Okay.
Clear? All right, so now what I'm going to do is I'll take this, plug it in here, substitute and simplify as much as I can. So what I will get is the following, is that my H is going to be minus J over 2 sum over I and J M squared plus delta Mi times M plus delta Mj times M minus B sum over I sigma I, where delta Mi is, again, sigma I minus M, delta Mj is sigma J minus M. Now, let me substitute this expression, simplify as much as I can. I will get J over 2 sum over I and J M squared minus J over 2 sum over I and J M sigma I plus sigma J, and then minus B sum over I sigma I, that this is equal to what? Is equal to J over 2. Now, this sum, well, each term in this sum is equal to M squared. Yes?
Why did you remove the minus sign in the first term?
Well, because you see, when I substitute here this expression, you see that I have M squared minus M squared minus M squared. That gives me globally a minus M squared. So this is what is written up here. Okay?
Yes.
So how many terms in this sum? N times Z. N is the number of lattice sites, and Z is the number of nearest neighbors to each lattice site. Then I consider the other term. So this is minus. Now, these two terms are identical, right? It's I and J are dummy labels, and therefore I get a minus J sum over I and J, M times sigma I minus B sum over I sigma I. So overall, I'll get J over 2 M squared N times Z minus J times M times Z plus B sum over I sigma I. Now the Z in the first term comes because for each I have to sum over all J's that are nearest neighbors to I. But you see that there is nothing dependent on J in this sum. So what I get is just the number of nearest neighbors, and that's it. So this is what I call the mean field Hamiltonian. And now, how do I solve the mean field theory? Well, in order to solve it, I have to know what is the value of this parameter M. But this parameter M, by definition, is the average magnetization. So it's 1 over N sum over I sigma I. And this can be computed by just computing the average magnetization with the mean field Hamiltonian. Therefore, at the end of the day, if you do this calculation, which is not difficult, you will get tangent hyperbolic of beta JM Z plus B. Okay?
Sorry, can you repeat the third last sentence?
Well, so what I'm saying is, in order to solve the mean field theory, you have to be able to compute this parameter M. But M is the average magnetization. So if I know the Hamiltonian, the mean field Hamiltonian, I can compute the average magnetization through this formula. And if I do this calculation, since now there is no interaction anymore, because all spins are independent, you see that the mean field Hamiltonian is an Hamiltonian of independent spins sitting in a mean field generated by all the others. So I can easily calculate.
Third last equation, actually, third last equation.
Sorry?
Can you repeat the third last equation? J by 2 square and Z, this equation. Minus J summation Ij yam sigma I, third last equation.
Minus JMZ. Which
Yeah.
one? This one?
No, third last. This one is second and third last. Yes.
This one.
No. Just above it, just above it.
The one above?
Yes.
You want to know how I go from here to here?
Yes.
Well, so here I have to perform this sum. So each term in this sum gives me a contribution M squared. And then I have to ask myself how many terms are in this sum. And their number is N, the number of lattice sides. And then for each lattice sides, I have to count the nearest neighbors, Z. And therefore the total number of terms is N times Z. Okay? Now here, this one comes because these two terms are essentially the same. I and J are dummy indices. They are summed over. And therefore, this is equal to twice sum over I and J M sigma I. And the 2 eats up this factor of 2 sitting here. And the rest is the same. Okay? Are you satisfied now?
Yes, thank you.
Okay.
I think in this line we can write just the sum over I because
we can. Oh, yeah, sure. Here. Well, No, let's keep the sum over I and j because I have to perform the sum over j explicitly in order to get this set. You cannot just forget it. All right, so this is my self-consistency condition. M equal to tangent hyperbolic beta jmz plus b. Okay? So now I would like to convince you of something interesting.
Sorry, I want previous page.
Yes? Can I go on?
No. Now you can go on.
Okay. All right. So so now I would like to convince you of something, that the self-consistency condition is actually a condition to determine the minimum of the Helmholtz free energy. Okay? So in other words, the solutions of the mean field theory are minima of the Helmholtz free energy. So this is very important to keep in mind. So how do I prove this? Well, it's very easy. Let me compute the mean field partition function, right? Which is sum over I sigma I e to the minus
Professor?
beta. Yes?
What do you mean by self-consistency?
Well, this is a self-consistency condition, right? M equal to tangent hyperbolic or whatever. Because what you're saying is the following. I'm making an expansion in the previous thing, assuming that my sigma have some average value plus some fluctuations. I write down what would be the Hamiltonian if this was true. And then this Hamiltonian has a free parameter, which is the average value, that has to be determined self-consistently. So I have to determine the average magnetization using the mean field Hamiltonian in which the average magnetization appears as a parameter. And I obtain this self-consistency condition. So all M's that satisfy this equation are actually solutions to my mean field theory. Okay?
Okay.
All right. So let us compute now this free energy. Well, it's a straightforward calculation. We know what is the mean field Hamiltonian. You will get JNZ divided by 2m squared times 2 cosine hyperbolic of beta JMZ plus b to the power n. Okay? Where n is the total number of lattice sites. So now, if I have this, I can compute what is the free energy. This is minus 1 over beta log z. And now I can try to minimize to find what are the minima of the free energy with respect to m. So what is the M, the magnetization M, that minimizes the free energy? Why? Because I know that M is a macroscopic variable, and I know that macroscopic variable, when I consider macroscopic variables, those are the one, I mean, I should look for minima of the free energy as to signify, I mean, as equilibrium states of my system, right? So let's do the calculation. dF dm. I invite you to do the, I mean, you have to make a couple of derivatives. You will get J n z times m minus the tangent hyperbolic of beta j mz plus b. So you see already from this equation that if I set this equal to 0, I get exactly the self-consistency condition I was talking about before, right? Because I have to set m equal to the tangent hyperbolic or whatever. So therefore, the self-consistency condition is a condition to find the minima of the free energy, right? To find actually the extrema of the free energy. But you don't know, once you find a solution to this equation, whether it's a minimum or a maximum. And the only states that are relevant thermodynamically are minima. Therefore, what you have to do is compute the second derivative as well. d squared f dm squared. This is equal to j n z times 1 minus beta jz plus beta jz tangent hyperbolic of beta jmz plus b squared.
Professor,
Yes?
can you repeat why do we have to find the extrema of free energy?
Well, that is something that we knew, that we obtained in thermodynamics when we defined the Helmholtz free energy. The Helmholtz free energy is, since the Helmholtz free energy is always decreasing when you make any transformation, then the equilibrium states are the ones consistent, are the minima. Given a set of parameters, the equilibrium states are the minima of the Helmholtz free energy. Okay? If you go back to the lecture in thermodynamics when we discussed thermodynamic potentials, you will find this statement there. So that's why I'm looking for minima of the Helmholtz free energy.
Okay.
All right, so I computed the second derivative, and now I have to find solutions to the first equation. And once I find the solution, I have to check that the second derivative is positive. Why? Because if the second derivative is positive, this is a minimum, it's not a maximum. If instead the second derivative is negative, this is a maximum, and therefore is not good, it's not an equilibrium state. All right, so let us set now b equal to 0. If we set b equal to 0, then we have that our equation is m equal to tangent hyperbolic of beta j times m, okay? And you see that this equation has always a solution. M equal to 0 is a solution. But the problem is that the second derivative of f with respect to m at b equals 0 is equal to J and Z times 1 minus beta JZ. And therefore you see that if JZ divided by KBT is smaller than 1, then the second derivative is positive. And m equals 0 is a solution, is a minimum. But if JZ over KBT is greater than 1, then d squared f dm squared is actually negative. And m equals 0 is a maximum. A maximum is something we don't want. So in other words, the free energy looks like this. Oops. So here I'm plotting the free energy versus m. It always goes to infinity for large negative and positive m. And then for temperature T greater than Jz over Kb, then m equals 0 is a minimum, and then the free energy is going to look like this. So this is what is known as the paramagnetic phase, because the magnetization overall is equal to 0. So the system is a paramagnet, and this is going to be a critical temperature, Tc. Now, when the temperature is smaller than this critical temperature, m equals 0 becomes a maximum. So the free energy will look like this, which means that the free energy is going to have two other minima that are symmetrical with respect to m equals 0. Let's sit one here and one there. In other words, there are solutions in which the magnetization is not equal to 0. And the fact that there are solutions for which the magnetization is not equal to 0 implies that the system becomes a ferromagnet. So this is the first time you see a phase transition, perhaps. I don't know if you have already done this, but this is actually a second order phase transition that happens at T equal to Tc. At T equal to Tc, the magnetization starts appearing in the system. And this you can see explicitly by solving, at least graphically, the system of equations. Because you see, so this is m equal 1. You see so let us draw the curve. So we have to solve the equation m equal to tangent hyperbolic of Jz over kbt times m. Now you see that this Jz over kbt is essentially setting the slope of the tangent hyperbolic at x equals 0. So if the system is, so if the slope is greater than 1, which means that you are below the critical temperature, then you see that you have three solutions to this equation. This one, and this one. This one is the m equals 0, 1 is going to be a maximum, and these are going to be the two symmetrical minima, m plus and m minus. And now you realize that as this slope gets smaller and smaller, and eventually you get to the critical point, these two m plus and m minus are going to be smaller and smaller in absolute value, and eventually are going to merge. So the magnetization as a function of temperature, as you go towards the critical temperature, is going to look like this. It's going to be positive, and then eventually is going to go to 0 at t equal to.
Sorry?
Yes?
What is the difference between the two graphs, the two green graphs? I mean,
Oh,
what's
here,
the
so
parameter?
here I have jz over kbt greater than 1, and here I have jz over kbt equal to 1. Okay? Now, let us now try to figure out how the magnetization behaves close to this point, close to this critical point. Now, it's not actually too hard to figure it out. Is just enough to rewrite the equation, the self-consistent equation, as m equal to tangent hyperbolic of Tc over T times m. Or, if you want, m equal to T over Tc arctangent hyperbolic of m, which is just the inverse of what I wrote down above. And this can be written as 1 plus T minus Tc over Tc times arctangent hyperbolic of m. All right? Now, this quantity here has a name in the theory of phase transitions. Is called reduced temperature. And is indicated by the letter little t, typically. Now you see that the magnetization is therefore equal to 1 plus t times the arctangent hyperbolic of m. Now, as you see, as t is small, so as t gets little t, as the temperature gets to the critical temperature, which means that little t gets smaller and smaller, the arctangent hyperbolic, the magnetization is expected to become smaller and smaller, to tend to 0. Therefore, what I can do is take the arctangent hyperbolic and expand it for m close to 0. What I will get is 1 plus t times m plus m cubed divided by 3. And now I can take this simplified equation, which becomes algebraic, close to the critical point, and solve it for m. And what I will get is that m is equal to 0, is always a solution, of course. And then there are two solutions, m equal to plus and minus 3t to the power 1/2. Of course, T has to be negative in order to find these other solutions, and T negative means that the temperature is smaller than Tc. So we discovered, therefore, that this behavior here is actually a square root singularity. M goes like minus T to the power 1/2. This is characteristic of mean field theory. Typically, what happens in general for any magnet is that the magnetization will go like minus T, close to this phase transition, minus T to the power beta. But beta, for a system that satisfies mean field theory, is equal to 1/2. In general, it doesn't have to be 1/2. Another thing we can calculate is the susceptibility, which is defined as dm dB. This turns out, in mean field theory, I'll let you do the calculation, to go like absolute value of T to the power -1. In general, it goes like T to the power minus gamma. Gamma is, beta and gamma are actually objects known in the theory of phase transitions as critical exponents. It turns out that these two critical exponents for mean field theory is predicting for these two critical exponents, beta equal to 1/2 and gamma equal to 1. Now, these critical exponents can be measured or calculated explicitly in many circumstances. So let me make a table to finish this lecture discussing an important thing. So in particular, so I can compute beta, or gamma in 2 dimensions, 3 dimensions, 4, 5, 6, 7, etc., etc., in all higher dimensionalities. I didn't put dimension equal to 1 because we know that in 1 dimension there is no phase transition, right? Now, let's see what are the critical exponents. The true critical exponents for the easy model in 2 dimensions. In 2 dimensions, I get 1/8, this is the exact result, and 7/4. The 2-dimensional easy model is exactly solvable, is another example of an exactly solvable model. It is actually exactly solvable because one can diagonalize exactly the transfer matrix. This is something that was shown by Onsager in the last century. It's a very important result, but it's not true for the 3-dimensional easy model. In 3 dimensions, there is no known solution, which means that you cannot write down the partition function analytically without doing approximations. So the critical exponents for the 2-dimensional easy models have been computed and are numerically, and they are approximately this. As you see, in both 2 dimensions and 3 dimensions, they are very different from the values given by mean field theory, which means that mean field theory is actually a very bad approximation in 2 and 3 dimensions. Fluctuations are much larger than what is estimated by mean field theory. However, what happens is that in 4 dimensions, these critical exponents are actually equal to the mean field ones. and in 5 dimensions and 6 dimensions and 7 dimensions and so on and so forth, they are always equal to the mean field value. Which means something quite interesting. It means that when you consider a physical system as since when you increase the number of dimensions, the number of nearest neighbors is increasing significantly. What happens is that at some point, the dimensionality is sufficiently large for mean field theory to be exact. And when it starts being exact, it's exact all the way over to infinity. So in the theory of phase transitions, there are 2 important dimensionalities to keep in mind. One is the dimensionality at which the phase transition starts occurring. We know that in 1 dimension there is no phase transition, right? For the easy model, but there is a phase transition in 2 dimensions. There is 1 in 3 dimensions. So this dimensionality at which the phase transition starts appearing is called the lower critical dimension. And then there is another dimensionality, which is as important, which is the dimensionality at which not the phase transition starts occurring, but at which mean field theory starts being exact, in the sense that it gives you the correct critical exponents for the phase transition. This is called the upper critical dimension. So you understand that if I would repeat the same game for the Potts model, for example, there would certainly be a dimensionality at which the phase transition is not there. In 1 dimension, there is no phase transition, as we know. But there will also be, for large enough dimensions, a dimensionality for which mean field theory is exact, simply because the number of nearest neighbors becomes huge. And therefore, you know, I don't remember now what is the upper critical dimension for the Potts model, also depending on Q, but this is a general phenomenon that happens for all systems, all available systems. All right, so I'm essentially done for today. So next time we will be talking about the grand canonical ensemble. Okay?
Professor?
Yes.
I'd like to ask something.
Yeah.
What if B is equal to B is not equal to 0? What would happen to all of this? Because the assumption a while ago is the magnetic field is 0. Yeah.
Oh,
So
if the magnetic field, you're asking me about, well,
yes,
so
yes,
if
yes.
the magnetic field is not equal to 0, then what happens is that the free energy that before was perfectly symmetric, well, it doesn't look symmetric, but imagine that it's symmetric. The free energy will become asymmetric. So will become something like this. So you're still going to have 3 solutions when the temperature is smaller than a certain temperature. But one solution is going to be more, is going to have a lower free energy as compared to the other. Okay, so this is the equilibrium state. And this one is a minimum of the free energy, but is not a global minimum, is a local minimum. Now, this is very important. Why? Because you see what happens. Let me make a graph. So you start from the symmetric state. Well, it's not symmetric. I would like to make it symmetric for once. You start here, and suppose that your state has a positive magnetization and is sitting here. And now I start putting a magnetic field and I make it asymmetrical. So the system is still going to be sitting here. And is going to be sitting there until I reach a certain magnetic field for which this is not a minimum, but actually a saddle point. At which point, this guy is not an extremum anymore, and the system will go to the other minimum. And now if I repeat the cycle back and I ramp up the magnetic field, I will go from this situation back to this, where this guy is now sitting not in the right minimum, but in the left one. This is actually the basic idea behind the phenomenon of hysteresis. The fact that when you look at the magnetization versus magnetic field, typically you have curves that are not always tracing the same line, but depending on whether you move up or you increase or decrease your magnetic field, the magnetization trace is going to trace one line or the other. And you have an area that is enclosed by these two curves. So there is a phenomenon called hysteresis that is connected to the fact that when you put a magnetic field, you have two minima of the free energy, but one is a global minimum and the other is a local minimum. The system keeps staying in the local minimum until it becomes unstable and goes to the global minimum. And then eventually the cycle can restart back. Okay, so this is what happens with magnetic field. Is it clear?
Yes, thank you.
Sorry, Professor.
Yes.
How can I simply define critical exponent?
Well, the way I defined it, you look at the magnetization close to the, as a function of the reduced temperature close to the critical point, and you ask and it's a power law. The behavior is a power law. The exponent is called critical exponent. And there are many, actually. I just defined two, beta and gamma, but there's alpha, beta, gamma, delta, eta, nu. There are many critical exponents in the theory of phase transitions, but I'm not going to go too much into the details because this is supposed to be a course in elementary statistical mechanics. Okay?
Okay.
Are there other questions? Okay, so if not, we'll meet on Wednesday for the next lecture. Okay? I think it's on Wednesday, correct? Let me see.
Yes.
Next lecture is on Wednesday. Yes. Okay, good. So we'll meet on Wednesday then. See you guys. Bye-bye.
Bye.